All right, let's use MLLib to actually make some movie recommendations using the MovieLens 100K dataset. So the first thing I've done is I've modified the dataset a little bit. So I've gone into the u.data file and added 3 entries for a fictitious user. And what these ratings mean, basically, is that I've created a new user ID 0, which is going to represent me. And this particular user loves Star Wars, which happens to be ID 50, and loves The Empire Strikes Back, which is 172. 5-star ratings on both. But for Gone with the Wind, which is movie ID 133, 1 star. Hate that stuff. So, I've basically made a persona here of a science fiction geek who, doesn't like historical romances, right? Not that hard of a person to imagine, right? So I would expect, things that are similar to Star Wars and Empire Strike Back, but not similar to Gone with the Wind to come back in my recommendations, okay? Let's see if it works. So, I have already imported the movie recommendations als.scala file from the course materials, and you feel free to run this yourself if you want to. And not a whole lot to talk about here that we haven't already talked about. We have the same function we've had before for actually constructing a map of movie IDs to movie names after parsing in the u.item file. That's all that function does. And down here is the same code that we looked at in the slides, so nothing's really different here. Just the usual boilerplate stuff for setting up your context, load up the movie name dictionary, and then the stuff we saw on the slide. We load up the u.data file, the actual movie ratings, and we map those ultimately into rating objects, which are part of the MLLib library that represents user, movie ID, and rating. And we cache that ratings RDD that comes back because it's going to be used more than once. We train a recommendation model just using als.train. It's just that easy, where we pass in the RDD of ratings and parameters for rank and num iterations. There's no real good guidance on how to set these, but I've tried, pretty much every recommended combination that's out there. And I've also looked up people who have actually done train test experiments to try to optimize that and find the optimal values. And around here is where it ends up. So that's kind of how I made an educated guess on those. We will take the user ID that we want to get movie recommendations for from the command line arguments, and then we will print out all of the ratings that we find for that user ID by just filtering that ratings RDD based on that user ID. And then we will actually call recommend products on the model that we had to actually get back the top 10 recommendations for that user ID and print them out. So let's see how it works. Now I've already created a run configuration for this script. I called it movie recommendations ALS, put in the usual stuff. We've done this enough times, you don't have to go through it again. The only thing different here is that I did add an argument to the arguments tab of 0, meaning that I want recommendations for user ID 0. So let's go ahead and run that and see what happens. Pretty darn quick. Did a lot of work there. I saw a little flash there of stage 25, so it's a very complicated job, and it's using a lot of complex machine learning algorithms there too. So what happened here? We loaded the movie names, we trained the recommendation model, and we said we want ratings for user ID 0, and here are that person's ratings. And like I said, Star Wars 5 stars, Empire 5 stars, Gone with the Wind 1 star. But the recommendations I got just don't make sense at all. I don't even know what some of these movies are. I mean, Low Down Dirty Shame came back as a top result, Endless Summer 2. I mean, some of these kind of make sense. Underworld, maybe, but the other ones are just crazy. And what's even worse is that if I run this again, I'm going to get a totally different set of results. There's kind of like a random component to this algorithm where you don't even get the same result more than once. I mean, there's definitely something going on here where there's some minimum threshold that should be in there that isn't, right? Like I'm getting from some very spurious results here. But I've tried all sorts of different parameters for it, and I just can't get it to be better. So, well, let's talk about what might have happened there in a little bit more depth. So what the heck happened there? Those results were terrible. And this is supposed to be the greatest movie recommendation algorithm there is. Well, it turns out that ALS is really sensitive to the parameters that you give it. But I've tried a bunch of different parameters for this, and like I said, people have done a lot of research on the right parameters to use there, and even those didn't produce good results for me. I've tried normalizing the ratings data, that didn't help either. So it just seems that this particular algorithm isn't a good fit for the 100K MovieLens ratings data to begin with. Honestly, I'm not even sure it's working the way it's supposed to. Those results are just so wacky, it's hard for me to believe that it's really doing the right thing. And this is a good example of where putting your faith in a black box algorithm like this can be kind of a dodgy thing. I don't really know what's going on under the hood. Sure, I can go look at the source code if I want to and reverse engineer it, but you'll notice that we got much better results just getting our own movie recommendations using our own algorithm that we implemented in Scratch without MLLib. And it's really not much of a leap to take that movie similarity script that we wrote and take it to the next level and actually find similarities for movies that I rated highly and combine them together for a list of recommendations. That would have produced far better results in this case. But remember too, when I was making those movie similarities by hand, the hard way, I did have to put in a bunch of minimum bounds for the number of co-ratings and things like that, and minimum scores, and those sorts of heuristics might not be present in the ALS algorithm, which causes it to bubble up a bunch of spurious results. But again, it's an example of where having more control and more in-depth knowledge of your algorithm can be a benefit. And it's also a great example of where complicated algorithms aren't always better. This is sort of a general lesson in machine learning and data science in general. Good data will always trump fancy algorithms. And the fancier the algorithm doesn't necessarily mean you're going to get better results. Often simplicity produces the best results. Another lesson here is never blindly trust the results that you get back from a machine learning algorithm. You always need to evaluate them yourself and look at them critically and measure, are they actually good results or not? And in the case of movie recommendations, that's a hard thing to measure, right? How do you actually measure quantitatively whether this is a good recommendation? It's really kind of an art to it. So in some cases, in this case, you could just take a look at it and say, this doesn't make sense, and something's wrong and needs further work. But sometimes the issues are a little bit more subtle, and you actually need to figure out, okay, how am I going to measure the effectiveness of these recommendations over time? What's the behavior I'm really trying to generate by showing people these things, and am I actually achieving that? And sometimes, the issue is the quality of your input data itself. So keep in mind, this is a relatively small data set that we're dealing with. It's also very old data, and probably people that are self-selected, probably mostly students at this college that was putting this project together. So lesson of the day, don't always trust algorithms that are outside of your control. More complicated algorithms aren't always better, and always make sure the data you're using is clean. So there you have it. But MLLib is still a very useful tool. So let's move on to a different example where it actually works better. And this is, on a simpler problem, regression. So let's talk about that next.